Welcome to Dr. PT's Chemistry Essentials, A-level chemistry made easy. In this video, we're going to be looking at directing groups on benzene rings and how they influence the reactivity. So from previous videos, we know that benzene has an electron density due to this delocalized pi system. So it itself is a source of negative electrons, and so it is attracted to electrophiles. And in doing so, it actually moves a pair of electrons from the delocalized pi system to the electrophile to form a new bond. And then from the mechanisms we've seen before, the hydrogen that was in the original benzene then breaks the carbon-hydrogen bond to reform that stable delocalized ring. So this step here, this second step, is very fast because it wants to reform this delocalized system. On the other hand, the slower step is this step here, and it's all down to the electronics. So the amount of electron density here dictates how fast and how likely this is going to happen. So we're just going to focus in on this step. And so the reactivity can be changed by changing the amount of electrons here. And that is all dependent on what substituents you have around the benzene ring. Now for our generic substituents, I'm just going to use X. And depending on what X is, we'll change the electron density of our aromatic ring and thus affect the reactivity when it's trying to make a bond with this electrophile. So there's two distinct types of X. There's what's known as electron donating groups, or EDG, and the other type are what are known as electron withdrawing groups, or EWG. So let's just focus in on what an electron donating group does to the pi system and reactivity. Firstly, the thing to identify electron donating groups are they all have lone pairs of electrons. So an example you've probably seen previously is phenol with the OH, with the oxygen having that lone pair of electrons. And then the other example is phenylamine with an NH2. Now it's these lone pairs of electrons on the oxygen and the nitrogen atoms that increase the electron density of the benzene ring. And because of this, it actually increases the electron density at specific positions. And these positions are at the 2, the 4, and the 6 positions. Now because of this, electrophiles, the E+, will either be substituted on these positions 2, 4, or 6. Now sometimes they will only actually substitute one of those positions, so there might be the 2 or the 4 or the 6 separately. Sometimes 2 positions are substituted and sometimes 3 positions are substituted. The example you've probably seen already, and it's in the previous video to this one on the playlist, is phenol reacting with bromine, and that forms the 2,4,6 tribromophenol product. And it was this reason of phenol being an electron donating group that we had these particular areas of the ring being functionalized and substituted. Now on the other hand, if our substituent X is an electron withdrawing group, then there's a different pattern of substitution. They are known as deactivating groups because they reduce the electron density of the benzene ring. The first reason is they have no p orbitals to overlap, so they can't start providing electrons because they're not a part of the system. And also, they are electronegative groups. So an example of an electron withdrawing group that meets these criteria is the nitro group. And what the nitro group does is, because it's highly electronegative, it pulls on the electrons that were in this delocalized ring and brings it out of the ring onto the nitro group. So what happens is you actually get an opposite of over here. You get a decrease in electron density of the benzene ring. Now, not all things are equal, and what actually happens is it takes electron density away mainly from the 2, the 4, and the 6 position. And so if it's taking electron density away from the 2, the 4, and the 6 position, that actually makes the 3 and the 5 positions relatively more dense with electrons. So they're more negative, 3 and 5. and so they're more likely to trap the electrophile. So what you happen to see is you see substitution at the 3 and the 5 position with an electron withdrawing group. So we can just simplify this whole idea here in terms of exactly which areas are substituted by removing the explanations and just giving you an example on each side. So here we've got phenylamine reacting with 3 molecules of bromine. I want you to just pause the video here and see if you can come up with the structure and the byproducts for this reaction. Okay, so you should have drawn this as the answer. So obviously very simple here because you can see it's an electron donating group through this diagram, but you'd memorize that. You'd see the amine in your molecule and you would know that you can only substitute at the 2, 4 and 6 positions because of being an electron donating group. And now if we turn attention to this nitrobenzene. So thinking back, pause the video here for this reaction and see what products that you can get. Okay, so we can see that we've got a Friedel-Crafts alkylation. We've got an alkyl group here. We've got halogen carrier, so we're going to add on these 2 carbons to the benzene ring. The product of that would be this molecule here, with these 2 carbons being these 2 carbons here. Now, the reason it's attached to this free position is firstly, it's an electron withdrawing group, so it'll only ever go on the 3 or 5. But you can see the 5th position here is already occupied by a methyl group. So there's no other room for any other groups to fit onto here. So that's already taken up, so we have to add it onto the 3. And then just for completion, obviously the byproduct would be HCl. Remember, the halogen carrier is catalytic, so this is regenerated through the reaction. Now, sometimes in the exam, you'll be asked to apply these concepts, and you'll be given enough information in order to apply these to a new scenario. So pause the video now and have a go at this exam question. Okay, so there's some important things in this question. First of all, it's telling us that only monosubstitution happens, and obviously this table is really key, because that's telling us the positions to which the new substituent is directed to. So our first one here, we can see we've got this CN, this cyanide, and we know that that adds to position 3. So you've got position 1, 2, and 3 here. It's important to always memorize conditions because we know we've got chlorine here and aluminium trichloride. So we're adding a chlorine on. So your product should look like this. Now the byproduct would, of course, be HCl, but it's only asking you to draw the benzene compounds here. And then with this one here, we've got this amide, which we can match up to this group here. We're told that we can get position 2 and 4, and it's asking to draw all of the organic products that could be formed. Again, because we don't need a halogen carrier here, because as you can probably see from the direction of it, it's an electron donating group, so it's highly electron dense. It doesn't need a halogen carrier to polarize the chlorine and to make an electrophile. It can polarize it itself. Whereas up here, the aluminium trichloride and the chlorine were needed in order to create that Cl+. So anyway, back to exactly what we've got to do. We have to substitute at the 2 position, and then we also need to substitute at the 4 position. Now, don't feel you need to number these at all. This is just for clarification here. You might be thinking, well, if we've talked about the fact that it can produce 2,4 as well, but this would not give you any credit because it specifically asks you to draw only mono-substituted products. So whilst this could happen, the question is limiting what choices and marks that you can get. Now, just one more exam question to bring some of all this together. Pause the video here and have a go at this one. Okay, so there is information within this question to help you answer it. First of all, it's telling you that the reactions of this aromatic amine, you can see it's aromatic because of the formula, and this is the amine group on it, are similar to the reactions of phenol. So you know that phenol itself is an electron donating group. And then you've been asked to draw the product from the tri-substitution of this aromatic amine with chlorine. So, knowing its electron donating group, you should know that substitution happens at the 2, the 4, and the 6 positions on the aromatic ring, and so you need to draw the product for that. Now, some of you may have struggled with the formula and converting this into this skeletal formula. Just always remember, you're always going to have, whenever you're dealing with aromatic chemistry, a aromatic benzene ring, and then it's the nitrogen that connects to there. And this brackets is telling you that those 2 methyl groups are attached to the nitrogen. Okay, and then in the more wordy 3 mark here, you're asked to explain why chlorine reacts more readily with this aromatic amine than benzene, and you're given a hint that it's similar to phenol. So the first part of this is the lone pair of electrons in the p orbital of nitrogen is delocalized into the benzene ring's pi system. This causes the electron density to be increased in the ring, and this in turn leads to chlorine being more polarized. And this is exactly why you don't need a halogen carrier with something that has an electron donating group in it versus needing it for anything that is just benzene or benzene with an electron withdrawing group. So this video has looked at directing groups and the effect that they have on substitution, and we've looked at both the electron donating and withdrawing groups. Hopefully you found it useful. If you have, ensure that you like the video and then ensure that you subscribe to the channel for new videos as and when they're uploaded.